Then, hello everybody, and welcome here. So, hello, Professor Glass, Professor Brook, Professor Roy, Professor Peterchev, and also everybody else who joined us here for the defense of Jinshui Zhang. He has come to us with a bachelor's from Tianjin University and a master's of Jiangsu University. Pretty outstanding results already, and has really thrived here at Duke, covering a wide range from electronics, power, biomedical engineering, and medicine. And I very much look forward to your presentation.
Hello, everyone. Thank you so much for coming here for my defense. This is my 5th year as a PhD student at Duke University, and my advisor is Dr. Goods, and I've also got a lot of help from Dr. Peterchev. Thank you guys so much. And my research topic is high power, high fidelity modular electronics for precise pulse generation, energy, and biomedical applications. I know it makes no sense to some of you in this room, but we're going to build it up step by step, and we'll go through some fundamentals. So I hope everybody can walk away having something learned. I want to spend the first 5 to 10 minutes to talk about power electronics, and then how we get to the modular power electronics. Power electronics is everywhere in our life. Our phone chargers, electric vehicles, data center, and power grids, they are all enabled by power electronics. It may sound a little bit overwhelming as power electronics can do so many things, but eventually they are doing only one thing. And that one thing is to convert the energy we have to the energy we need. The input and output of power electronics can be very different. For example, our phone charger needs to produce a 5-volt DC output from a 110-volt AC input. And our electric vehicles need to convert 400 volts from the battery to an alternating 300 for the motor. And we can list thousands of different examples. But now let's look at a simple one. Here we want to get a 50-volt output from a 100-volt input. So how can we bridge this difference? Well, the easiest solution is to throw the actual 50 volts away, and that's how linear power electronics work. It works for some low power scenarios, but not for any high power applications. It just wastes too much energy. So here we lose as much as we get. So instead, all the high power electronics are built on switching mode. And here is how switching mode works. So this is a graph of the output voltage over time. What we have at the input is either 100 volt or 0, and what we desire at the output is 50 volt. Like this red dash line, and it's also called the reference. And switching mode power electronics jumps between the 100 and 0 to use the average value of the output to track the reference. So to do that, we only need 2 switches to connect and disconnect the input and the output. So when we turn the top switch on, the output is 100 volt. And when we turn the bottom switch on, the output is 0. And we can alternate them back and forth. And this way, we get an output that follows the 50 volt reference by jumping between 0 and 100. And this is the fundamental idea behind everything today in this presentation. So take your time. And sometimes the reference is more complex than a simple constant. It may fluctuate like in a power grid or electric vehicle, and we can change the good ratio to track it. Also, it's not always necessary to switch very fast. We can also allow the switches to be lazier, like this. So this choice between lazy and basis switching will be a central topic in one of our later sections. But for now, let's just stick with this simple approach to build up more basic concepts. Let's talk about switches. I mean, they are the reason why switching mode power electronics exists. And here is how they look like in real life. They're also called transistors or power semiconductors. And I only need you to know about two things about them. The first, they are expensive. And second, they're easy to break. These switches have their limits on how much voltage or current they can handle. Once beyond that range, they break. For example, if the switches here we are using are rated for 100 volt or higher, we can easily make this circuit work, no problem. But what if the input voltage is 500 volt? Well, they break. And this challenge is what led us to the idea of modular power electronics. So if one circuit can only handle 100 volt, how about putting five of them together? And then every circuit can operate the same as before. And then we add their output together, we get the same output as before, except the amplitude now is 500 volt. So this idea works, and it is that easy. But before we wrap up, we can actually make things a little bit better. So instead of switching all of them at the same time, what if we slightly interleave them? Can you imagine what the output would look like? Yes, it's a staircase. And the more modules we have, the more stairs we will get. And the closer the output can track the reference. So congratulations, you guys just have all learned how modular power electronics works. And if you are satisfied, you can walk away with some snacks. But if you want to learn more, you can stay. So essentially, we break down a massive power or voltage and build small units we call modules, put them together, control them independently, and get a staircase-like output and use that to track the reference we want. And eventually we get the power that we need. And to my eyes, there are three fundamental ingredients of modular power electronics: topology, hardware design, and control. Topology generally means the structure of a circuit. In this presentation, it refers specifically to the structure of a single module. For example, here, our topology consists only two switches, and in the next section, we will see more variations. And hardware design is how we turn modules from paper into reality. It usually involves the simulation, the CAD design, manufacturing, and testing. And now we have our modules. The next step is to operate them, to turn them on and off at the right timing. This process is called modulation. So modulation usually involves multiple metrics. In this presentation, I will mainly study how to make the output track the reference better. That's a quality we call the fidelity. Okay, so we just covered some background and fundamentals of power electronics. And now we're going to move to my research. And like a typical dissertation, mine consists of several research topics. So we just split the design of modular power electronics into three areas: topology, hardware design, and modulation. I have made a unique contribution to each of these subfields, and we're going to talk about them individually. And after that, I'll show you some applications that build on the combination of this research. So before we move on, do we have any questions? Then I'll start my first research. My first research is on topology. And research on topology sometimes may look like a kid's game, because what you are doing is actually just to place transistors and components at different places and see if they work. However, it really surprised even myself that after so many years of modular power electronics development, there is still something for me to discover. And what I discovered is actually a treasure. This new topology can provide functions that used to be only possible with double number of transistors. And now we're going to build it up step by step. So in our introduction, we have seen a simple topology. This one with only two switches. and this is called the half bridge. This is what a half bridge topology looks like in the language of modular power electronics. We have power semiconductors to switch voltages. We also have capacitors to maintain the voltage at a stable level. The half bridge is one of the most popular and probably the most important topology because it works and it's just simple. There's another important topology called full bridge. So compared with half bridge, the full bridge topology has two significant improvements. First, it adds more output levels. Beyond positive and zero, it can now give us also a negative output, like here. And the second, also the most important advantage of the full bridge is how it handles a short circuit fault. When the fault happens and we must turn off all the transistors, the half bridge can only block one direction of the fault current. And the fault on the other direction will spread further and cause more damage to the power system. But the full bridge can block both directions, so they are irreplaceable in many power systems. So these two, the half bridge and full bridge, are two foundational and most widely used topologies in modular power electronics. We also have different bridge circuits invented ever since. Some of them add diodes or transistors to the half bridge to get a DC fault tolerance, like the ones in the middle. And some others add even more transistors to the full bridge to get more output levels, like the one on the top. However, except the half bridge and full bridge, most of these topologies have only stayed on paper as a research outcome and have never been truly recognized by the real world. And there's a reason for that. These topologies offers nothing new, but only more output levels or fault tolerance. However, these functions already come with the full bridge topology. If we need more levels, we can just throw in more full bridge modules. So why bother making the circuit more complex when the simple solution already works? It's not worth it unless we're getting something really brilliant and unique. And what could it be? So before answering that, let's zoom out and look at the detail that we have been missing. We have seen these slides a lot of times because I've spent a lot of effort on it. I want to reuse it over and over again. But there's one thing we have always taken for granted. We have always assumed that for the total 500-volt input, each module will carry the same share of the voltage. In this case, every module would have a voltage of 100 volt. But that's almost never the real case. When we insert a module into the output loop, we're actually charging or discharging them with a load current. And this process is different for each module. As a result, some modules may accumulate more energy than others, which means a higher voltage, like this module on the top. And if this difference grows too large and the voltage gets too high, it will damage the module, even the whole system. So we must keep all module voltages close to the same level. And here is how the mainstream solution works. Basically, we measure the voltage of each module and sort them, and then let load current discharge the high voltage modules and charging the low voltage ones. So basically, we feed the skinny cat and put the overweight cats on a diet. It works in theory, but it has two major issues. First of all, sensors are not always reliable. They're easily affected by temperature and they age over time. And second of all, the sorting process is quite time consuming. We can't do it fast enough if we need a rapid output response. Okay, so this is interesting, but wait, are we still talking about topologies? It sounds like a total software problem. Yes and no. Yes, what I just described is a software problem. Actually, the software causes us problem. But does it have to be? The answer is no. So in all the topologies we have seen, there's only one connection between modules. We can either include the capacitor in the output or switch it out and let it idle, do nothing. But there's no direct interaction between modules. They're like two neighbors living next door but never visit each other. But what if we have two connections between modules? We could still do everything we wanted, but now we gain a superpower. When we switch the modules like this, we actually parallel two modules and their capacitors to supply one voltage level. And when capacitors are connected in parallel, they automatically equalize their voltages. So now with this structure, we can balance modules with only hardware and no need to worry about sensors and algorithms. So this is our new superpower. And this topology is one of the earliest capable of this parallel trick. Its name is cascade double H bridge circuit, or CH2B. It had 8 transistors and 1 capacitor. It's invented by my advisor about 10 plus years ago. Good job. And here is how we connect two CH2B modules together. And we can operate CH2B modules with 6 different active modes. In this mode, two modules are connected in series, supplying a positive voltage to the output. And in this mode, they are connected in series with the opposite polarity and give a negative voltage. And in this mode, two capacitors are in parallel, which is what makes CH to be so special. And same here. And we also have two modes that capacitors are connected at the same pole and being bypassed and contributing nothing to the output. So this is how CH2B topology works. And it's a very competitive, but slightly luxury alternative to the full bridge. The biggest advantage of CH2B is automatic module balancing with no sensors or algorithms, very robust and reliable. And it's certainly a new landmark in the innovation of module topology. It has unlocked a new dimension of the functionality, the parallel module connection. So even at a price of a large number of transistors, this topology is still very remarkable. Well, of course, all this amazing work has nothing to do with me. They're just the giant shoulders that I'm standing on. But because of these previous works, I was able to ask one question. So can we use only half as many transistors to do the same thing? Nah, this sounds too good to be true. Until I accidentally discovered a new topology that I'm going to show you. So 2 years ago, I was sketching the CH2B topology on paper to prepare for some presentation. And then I got distracted and wondered, what if I just replace one transistor with a diode? It seemed to work with a slight compromise. And then I replaced another one and then another one. And eventually, I got a new structure that does almost the same thing as CH2B, but needs only 4 transistors, half as many, and the same as the full bridge. You are seeing this topology right here. It has 4 transistors and 4 diodes, so we give it a name of 4T4D topology. And compared to transistors, diodes are much cheaper, and they don't need auxiliary circuits like gate drivers and power supplies for gate drivers. And because of that, the cost of this circuit is not just below CH2B, it's actually very close to the full bridge, but its functionality is almost as good as CH2B. And this is how we connect two 4T4D modules together. And similar to CH2B, the 4T4D structures have 6 active modes. They may look similar, but there are some subtle differences. One of the difference is the current path. Although each mode appears to have 2 branches for the load current, sometimes only one path is active. So here are the paths for the series plus mode. For one current direction, we have 2 paths on, and for the opposite, only one path is active. And we have the same situation for the series minus mode. And in parallel modes, there's only one path for the low current. Same here, and also only one branch active in the bypass modes. So this difference in current path means 4T4D has a slightly higher conduction loss than the CH2B. However, it's still better than the full bridge. And another difference is how the modules are paralleled. Both Sage2B and 44D has two paralleling modes, but Sage2B supports bidirectional paralleling in both modes, while 44D supports only one direction for each. So this is the parallel minus mode of 44D, where the capacitor on the left is charging the capacitor on the right. And this is the parallel plus mode. The capacitor on the right is charging the capacitor on the left. So when using the 44D topology, we must alternate between two parallel modes from time to time, which we do already for the Sage2B to even the stress on the transistors. And so this is the basics of this new topology. It has a similar functionality to the Sage2B, but a cost close to the full bridge. And we will see an application using this topology later. And it's certainly an outlier in the trade-off of topology innovations. It's the first and I think very likely the only four-transistor topology that can generate bipolar output and fully block current and support bidirectional paralleling between modules. And also this topology has won us the best presentation award at the 5th IE conference at Chicago. So, and this is what we have learned from this section. So topology design is always a trade-off between functionality and transistor count. With the invention of Sage2B, people unlocked a new dimension of functionality, the parallel connection. However, this feature used to cost us 8 transistors per module, but we, with this new topology, cut it down to 4. And in a bigger picture, to be honest, the half bridge will probably remain the most popular topology. However, I believe our new topology can compete with or even replace the full bridge. And yeah, this is the first section. And if there's no question about the topology, we'll move on to the next. So in the topology design, we have talked about how amazing topologies like Sage2B or 44D are, as they can balance modules with no sensors. However, they have their own problems. They might face a current surge when putting modules into parallel, and this current surge could be a hazard if not handled properly. This concern is also common in other circuits like switched capacitor. And in this section, we will look at some existing solutions to this problem and my contributions to make them more compact and friendly to use. This is what's happening when we put modules in parallel. We're basically connecting two capacitors through nothing but two transistors, which gives us almost no impedance. So if they have different voltages, even just a tiny difference, there will be a huge current. And this is the equivalent circuit of this phenomenon. We have resistance and inductance from the parasitics and transistors, and sometimes also a diode if we're using IGBT or diode-related setups. The resistance and the inductance are very small, and so the current is huge. The paralleling current may oscillate or decay depending on the ratio of RLC, but their first cycle is always a high surge, potentially much higher than what the transistor is designed for. And a large current surge, even just a brief one, can drive the transistor into saturation and damage them. So how can we reduce or limit the current surge? Well, we can always increase the resistance like here, but that dissipates energy through heat, which means power loss, and we don't want that. The other option is the inductance. Inductors can impede alternating current with no loss, which makes it a better solution. And here are some commercial inductors. If you have ever been curious enough to disassemble some old electronics, you have probably already seen them. And here's another inductor you might have seen more often, but never realized it. This black block on our video cable is a Farad clip. When clipped onto a signal line, it adds inductance to suppress noise, although we don't usually see them in high power applications. So let's go back to these standard inductors. The problem with them is that Yes, they add inductance to the parallel loop, but they also add inductance to the output, which makes the circuit slower and harder to control. And we want a better solution that has no side effects on the output. And this better solution is differential mode coupled inductor. Here is how it works. Two wires are wound onto the same magnetic core such that for common mode current, which flows in the same direction in the wires, the flux they generate cancel each other out, and the core has no effect on them. But for differential mode current, they flow in the opposite direction, the flux adds and reinforces, which creates a high impedance. So differential mode current is impeded, but common mode current can freely pass. And this is a great match for our need. In our module circuit, the load current flows through the inter-module connection in the same direction. So this coupled inductor will not increase the output impedance. But the paralleling current flows in the differential mode direction. And here, the coupled inductor will add significant inductance to that path, which limits the current surge. So now we have a solid solution. To insert a differential mode coupled inductor into the intermodule connection, the next step is to make it. We have mentioned earlier that power electronics fundamentally solves only one problem, the mismatch between input and output. But there are actually many other important metrics. One of them is to make things small. Just think how our laptop chargers have shrunk over the year. So smaller electronics are more portable, cheaper, and for high frequency applications, smaller sizes usually mean fewer parasitics, which improves efficiency and quality. So in this section, we will propose two compact solutions, which are my main contribution. The first solution, we realized that PCB or printed circuit board is a good material for our inductor idea. They're very compact, easy to design and manufacture. We have two PCB inductor configurations. The first one forms a flux that is perpendicular to the PCB plane. And it gives us a higher inductance, but also more resistance. And the second one forms a flux parallel to the PCB plane, which gives us lower inductance, but also lower DC resistance. And here's how this PCB coupled inductor work on our prototype. This prototype is a 3-module inverter built on gallium nitride transistors and CH3 module topology. Its dynamics are very fast, and in later sections we'll explain why. And a tiny inductance can make a huge difference. We have the final design in the middle picture. If I hadn't highlighted, you would probably barely notice the PCB inductor at all. And that's the charm of PCB inductance. They're very compact, flexible in shape, and extremely cheap. And they're very effective. So on the right, we have the test waveforms. From top to bottom, the pictures compares the output voltage, module voltage differences, and paralleling current. For the same working conditions, after inserting the PCB inductance, we reduced the current surge from nearly 100 amps down to just 12, which could have saved transistor from being damaged. So that's our solution number one. We inserted just a small piece of PCB and made a huge difference to the current surge. But we did introduce actual resistance and wiring into the system. My next question is, what if I don't want to insert anything at all? I mean, it may sound like a greedy demand, because how can you add inductance without lengthening the wire? Look, all the inductors, they all need wires. Well, there seems to be one exception. The clip-on ferrite adds inductance without changing the wires at all. But the problem is the clip-on ferrite only works for common mode current. If we use this, it will only add more impedance to the output, but cannot help with the current surge, which is the opposite to what we need. So can we change it? Yes, and here is our solution number two. So imagine the ferrite coil is not a rigid piece of metal. Instead, it's as soft as a piece of dough. And now let's grab it, twist it, and then put it back onto the wires. So can you imagine what we're getting? We get this figure of eight-shaped magnetic core. In this design, we are not winding the wires onto the magnetic core. We're actually winding the magnetic core onto the wire or busbar or any other conductors. So in this way, we get a clip-on ferrite that gives us differential mode inductance without touching the wire at all. And we run a simple simulation in COMSOL to verify this idea. When the wires carry common mode current, their flux cancels. And when the core has a very low magnetic field, so it gives almost no impedance. And when they carry differential mode current, like the one on the right, their flux adds to each other and produce a high magnetic field, and therefore high impedance around 1.5 microhenry. And of course, making such a complex shape from ferrite is not easy since it's a fragile material. But we found a way to fabricate in the lab. We use water jet to cut small pieces out of a ferrite plate and then glue them together with epoxy. So this is eventually what we got, and it works pretty well. We eventually validated this design on a prototype, which is a 3-module CH2P inverter. And here on the right side, we have waveforms of output voltage, intermodule current, and module voltages. Black curves are without magnetics, and the red curves are with magnetics. This inverter has a very low power. The module voltage is only 5 volt, and the output current is well below 1 amps. However, even with such a low power, without magnetics, the intermodule current could easily reach 20 amps. And with the ferrite, we immediately reduce it to a third of it. And we can further reduce it by throwing more ferrite. It's very easy to scale. So this is our work on intermodule magnetics. We first identified the current surge problem, and differential mode magnetics seems to be a decent solution. And our contribution is 2 compact magnetic designs. One is based on PCB. It's very cheap, it's customizable. And the other one is inspired by clip-on ferrites, which can be added to any existing system without breaking it apart. Yeah, so do we have any questions? All right, so we're moving on to the next section. In the last 2 sections, we talked about how to design and make modules. And in this section, we will talk about how to operate them, which we call the modulation. There are already tons of work on the modulation for power grid applications, which operate at a low output frequency. However, there is still a lack of efficient modulation schemes that maintain high quality over a wide spectrum. And this capability is essential for reproducing arbitrary signals or complex signals, such as needed in pulse generators or amplifiers, which we will cover in later sections. And in this section, we'll combine 2 existing technologies with a secret ingredient to make this possible. We mentioned earlier that there are 2 different modulation strategies, the busy one and the lazy one. At the top, we have the busy approach. It compares the reference with a fast triangular waveform and producing a rapidly switching output to approximate the reference. And we call this the PWM approach, pulse width modulation. And at the bottom, we have the lazy approach. The output is simply snapped to the closest level, switching only twice per cycle. And in modular circuits, it gets a little bit more complex because there are multiple modules. So for the PWM approach, this means we have 1 carrier per module. Depending on how we place these carriers, we can have different variations, such as phase-shifted or level-shifted carrier methods. And the lazy approach also gains more flexibility with multiple modules. The basic version still runs to the nearest level, And we can also fine-tune the switching timing to eliminate specific harmonics. So in this section, we will talk about their performance towards a wide output bandwidth, which is important to get a better quality for arbitrary signals. Let's start with the carrier-based PWM methods. This graph on the right shows how distortion changes with their output frequency. PWM methods are great for low frequencies, have a very low distortion. But as the output frequency increases, their distortion gets worse. And the only remedy is to raise the carrier frequency, which eventually gives us more switching loss and sometimes even hit the physical limits of transistors. And the fundamental switching approach always have a consistent quality because their output always have the same shape regardless of the frequency. But they have a much higher distortion at low frequencies than the PWM approach. So PWM is better at low frequencies, and nearest level modulation is better at high frequencies. They both have a clear weakness in the other's territory. Now we know what our expectation should be. If we want the best quality over the full spectrum, we would want PWM performance at low frequencies and nearest level performance at high frequencies, just like this dashed line. And it's natural to consider combining these two methods together. And some people already done this, which gives us the nearest level PWM. And here's how it works. The base is still the nearest level modulation. It runs the signal to integers, but this produces residues. And the original nearest level modulation simply throws them away, which is why its distortion is higher than PWM. The information in the residues is lost. But nearest level PWM adds a 1-bit PWM here that takes this residue and compares it with a carrier and adds its results to the nearest levels and hope to get the lost information back. It sounds promising, but there is a problem. So remember what we said about carrier PWM? The carrier must be much faster than the reference to work well. But here, the residue is much faster than the original reference signal. So it very easily approaches the carrier frequency, which makes this 1-bit PWM collapse. We originally added the PWM section to improve low frequency performance, but now it causes even more trouble at high frequencies. And our contribution is very, very simple. Before sending the residues to the 1-bit PWM, we add a low-pass filter, and this filter keeps the PWM modulator within its comfort zone. At low frequencies, most of the residue passes through to the PWM and giving us better quality than nearest level alone. And at high frequencies, the filter removes the components that PWM cannot handle and only passes what it can manage. So basically, the low-pass filter is a safeguard for the PWM. And this idea does work. We tested our theory on a 3-module circuit. The results are on the right. The x-axis is the output frequency, and the y-axis is the distortion. We gradually increase the output frequency from very low up to the carrier frequency and measure how each method can hold up. And the lower the distortion, the better the quality. The black curve is the phase-shifted carrier PWM, and red is the nearest level modulation. Blue is the NL PWM, and green and purple lines are our proposed methods. The PWM approaches collapse at high frequency, and nearest level modulation holds a constant distortion level. And our approach maintains a low distortion over the full frequency range. The difference between green and purple is green used a causal filter, which introduces a delay, and purple used a zero-phase filter with no delay. It has a better performance and it requires knowing the reference signal in advance, which is good for generating a pulse, but it becomes kind of limited in grid applications. So in this section, we analyze the strength and weakness of PWM and nearest level modulation, and then combine them with a filter in between. This modulation scheme promises us a good quality over a wide output bandwidth, which is significant if we're dealing with arbitrary or complex reference signals. So we have covered the fundamental research, and let's see now how these technologies can be translated into real applications. Our first application is an equipment for the power grids called StatCom. We all know that clean energy is becoming essential for our life. Wind, solar, and our renewables are the future. But unlike fossil fuel plants, these energy sources are unpredictable, and this is causing more and more instability in our power grids, especially in terms of voltage. StatCom is one of the key technologies to address this problem. And they usually prefer a modular structure to deal with massive voltage and power. In this section, I'm going to introduce a new StatCom solution with our 4040 topology to take care of the module balancing problem, which can make the system more robust and reliable. Let's first see how a StatCom works. So here is a very oversimplified description of how electricity is transmitted. The power plant is far away, and the power grid carries the electricity over to our house. However, the power generated by the plant does not always match what we need. Think of the power grid as a water pipe. When the generated power is less than what's needed, the grid voltage, just like the water pressure, will drop. And when the generated power exceeds what's needed, the voltage rises. We don't want either situation to happen. Both are bad for the grid and for our appliances. So people introduced a device called the synchronous static compensator, or StatCom. We can regulate current of StatCom to exchange reactive power with the grid and eventually to stabilize it. We have established before that modular multi-level converter is a good solution to deal with its massive power and voltage. Sometimes it can reach tens of thousands volts. But one of the main challenge is modular StatCom. It's the reliability of sensors and software. And that's where our new topology comes in. So here we propose a new StatCom design, like a conventional modular StatCom. Several 4040 modules are connected in a string and hooked to the power grid through an inductor. Overall, this converter controls their voltage to regulate the reactive current they inject or absorb from the grid. And we built a 3-module prototype with this structure. Here is the circuit and its specs. It's designed for a low voltage emulated power grid in our lab. And here is how we control this StatCom. We have 2 control loops. The inner loop regulates the output current, and the outer loop regulates the modulation depth, which is equivalent to controlling the module voltage. But this way, we can get rid of all the module sensors. And we validated our design with our prototype. Here are the steady state results. The top waveform shows the output voltage, which is the black curve, and current is in the red. Both are in good sinusoidal shapes. And the bottom shows 3 modules voltages. They're well maintained and balanced around 40 volt. And we did another test of current step. We changed the target current from 2.5 volt to 2.5 amps to 4 amps. And the current immediately tracks the reference, and the voltage settles to a new stable state with no overshoot or oscillation. And we did another additional test to verify our control idea. We stepped the modulation depth reference from 0.5 to 0.8. In our theory, for the same output current, a higher modulation depth means a lower module voltage. And this test confirms it. at depth 0.5, the module voltage is regulated around 60 volt. And when we change it to 0.8, it drops to around 40. So this is the first principle explanation for why our control scheme works. And here's what we did in this section. The modular power electronics is a great framework for StatCom applications. And SAGE-2B topology was introduced several years ago to simplify sensor needs. And but the price is 8 transistors per module, and it still requires one sensor for each arm. And we replaced the module topology with 4T4D, so we only need half as many transistors. And we also improved the control approach to get rid of the last sensor. So do we have questions before the next application? And our next application is a power amplifier. A power amplifier takes an arbitrary signal and reproduces it at a much higher power level. This technology is common in audio equipment and medical imaging systems. In this section, we're designing a power amplifier for a neuroscientific research, specifically to drive the precise high power signal that brain stimulation needs. And here's a big picture. We have nanoparticles that can activate specific neurotransmitters when stimulated with magnetic wave at a specific frequency. When we inject these nanoparticles into mice and stimulate their brains with waves of different frequency, different neurotransmitters might be activated, which can induce different behaviors in animals. So eventually, it might look like mind control. And our work in this study is the power amplifier that drives the coil. The challenge is very demanding. We need a combination of kilowatts of power and a very wide output bandwidth, from kilohertz up to megahertz. And here is a survey of existing power amplifiers. And what we need here is an outlier. However, we realized that the combination of a high power and high output resolution is actually a sweet spot for modular power electronics. More modules can give us more power, but also give us a better resolution. The tricky part is MMC, or modular power electronics, usually operate below kilohertz, but what we need here is to reach several megahertz. And also we need to keep all module voltages balanced to a similar level. And our solution is to combine the SAGE-2B topology with fast switching gallium nitride transistors. Gallium nitride can switch at megahertz with ease, and that's actually the technology inside our laptop chargers, why they're so small. And on the other hand, SAGE-2B topology can automatically balance all the modules, so we don't have to worry about module balancing. And here is our final system. It has 7 modules, each with 3 boards in parallel. And with this design, we can generate the multi-channel stimulation we wanted. Here is an example. On the right side, we have the waveform of the voltage and current, and the bottom is the current spectrum over time. Its x-axis is the time, and y-axis is the frequency channel. And the color here corresponds to the intensity of the frequency components. The brighter it is, the more intensity it has. For example, from the beginning to 0.1 millisecond, we start with one frequency channel around 100 kilohertz, which has a bright color compared to the rest. And from 0.1 to 0.2, we added another channel of 200 kilohertz, so we can see 2 bright traces. And we have 6 different frequencies from 100 kilohertz up to 5 megahertz, all mixed in at different timing. And these different frequency channels can be used to activate different nanoparticles. And this multi-channel test would have been the end of this section. But then I realized we can actually do something more entertaining. With the same machine, I generated another pulse. This may look very random to you, but if you analyze its spectrum, things get a little bit more interesting. There is actually a picture hidden in its spectrum with 23 frequency channels. I mean, I don't have enough time to explain what this is. You might have to find out yourself. But this test is only to show off how flexible our machine is. And I honestly cannot think of any practical use of it, but I'm entertained. So this is our work on a high power amplifier with an ultra wide output bandwidth. The key technology is to combine the CH2B topology with gallium nitride transistors. Any questions before we move to the last application? Great. And here comes our last, but certainly not the least application, transcranial magnetic stimulation, or TMS. This technology is widely used to treat mental disorders such as major depression or OCD. And here's me testing TMS protocols on myself in the lab. Yeah, we do this a lot. In the past few years, people have attempted to use modular power electronics to make TMS more flexible. It's a decent solution, but it costs a fortune. In this section, I will introduce a new circuit concept that can make modular TMS solutions a little bit less overwhelming. So TMS works by stimulating our brain with rapidly changing magnetic fields. One of the core components is the pulse generator. And because stimulation must reach our brain wirelessly but deeply through our scalp, skull, and tissue, it requires a high intensity, typically several kilovolts and several kiloamps at the same time. The pulse width is usually below half a millisecond, which means the output bandwidth is higher than 20 kilohertz. And here is how state-of-the-art TMS pulse generators have evolved over the years. In type A and B, we have resonant-based circuits, essentially discharging a capacitor through an inductor, and they use thyristors, which can handle high current, but cannot be actively cut off. So the pulse shape is very limited. We get what we were given, we cannot control it. In type C, TMS began using more controllable switches such as IGBTs, which allows the current to be cut off. And this enabled control over pulse duration. And type D pushed the flexibility to another level with the help from modular power electronics. By stacking many modules together, we can synthesize almost any pulse shape that we can ever imagine. Like here, we have a staircase, but we can also generate a white noise waveform. It's clear that these technologies are leading us to a future where TMS can be more flexible so we can explore what's better or what's more effective for our patients. However, if you see the actual machines side by side, you immediately notice there is a price for flexibility, size, and cost. In our lab, we have almost all the commercial machines and also two most advanced modular TMS machines in the world. The first thing you will notice about them is they are really huge. A modular TMS machine can take the space about half a closet, but commercial TMS machines are much smaller. Some companies can even make it fit into a suitcase. And when you open them up, you will know why they're huge. There are just so many modules inside. Here in this slide, the middle one has 10 modules, and the one on the right has 6 modules. And there are legitimate reasons for having so many modules. First of all, TMS has a very high voltage, several kilohertz, but that's not the real bottleneck, as we have more high voltage transistors thanks to wide bandgap materials such as silicon carbide. The real bottleneck is the output resolution. Because these signals eventually goes to our brain, we absolutely don't want any unknown harmonics or distortion interacting with our brain cells. We need to synthesize these pulses very precisely. And remember, the more modules we have, the more staircases we have, and the better the resolution will be. So it seems like we have no choices but to use many modules. In this section, I want to answer one question. So can we achieve a good resolution with fewer modules? And first, let's understand why we need this many of modules. Let's go back to the very basics of modular power electronics. Assume we have 3 modules here, and each of them is capable of an output of +1, 0, or -1. And the system output can range from -3 to +3, which gives us 7 levels in total. Very simple math, right? But if you look at it from another angle, it's puzzling. Since we are controlling each module independently, there should be 3 times 3 times 3 equals to 27 possible states. It's also very easy math. So why do we only get 7 levels instead of 27? And here's why. For example, if we make the first module generate positive and the other modules generate 0, we get an output of +1. And we get the same results here if the module 2 is +1. And same here, if we get different numbers, but their sum is 1. So several other states, like this one, all point to the same output voltage. And this redundancy is that different output states point to the same voltage is why we have only 7 output levels instead of 27. So can we get more output levels with the same number of modules? And the reason why we have so many redundant output voltages is all the module voltages are the same. However, once we jump out of that framework, we can get a very different result. For example, if module 1 has a voltage of V, module 2 has 3 times V, and module 3 has 9 times V, guess how many more output levels do we get? Exactly 27. And an amazing resolution. It would have such a good resolution that its steps are barely visible anymore. In practice, we don't have to strictly follow this 1/3/9 ratio because it might make the hardware design more challenging, but we can pick different ratios depending on the reference signal. And we built a small prototype in our lab to demonstrate this idea. This machine you are seeing has roughly 1/6 of the power level of a commercial machine. And this system has 3 modules with SAGE-2B topology and silicon carbon transistors. And we also built 2 other machines with the same material, but they are running with equal voltages. And one has 3 modules, another one has 6. For each of these 3 machines, 2 symmetric and 1 asymmetric, we use them to synthesize 3 different pulse shapes, monophasic, biphasic, and Gaussian polyphasic, and we measure their total voltage distortion. For all 3 pulse types, our 3-module asymmetric solution has the lowest distortion, which means the best performance. It's even better than the 6-module symmetric system. That's twice as many modules, but our solution still beats it. So to wrap it up, in this section, we explored how to use fewer modules to obtain a better output quality. And this technology would offer us an easier access to flexible TMS treatment or research. So I think that covers most of the technical work I've done over the past 5 years. And for the fundamental research, we have a new topology, which is a potential replacement or upgrade for the full bridge, one of the 2 fundamental topologies. And we have 2 very compact magnetics designs to deal with current surge in parallel MMC circuits. And for modulation, we proposed a new approach that can allow us to handle more complex or even arbitrary reference signal. And based on these technologies, we built 3 applications: a StatCom with strong potential for power grids, a very flexible power amplifier for neuroscience research, and a new TMS solution that achieves better quality but with fewer modules. And here is a list of all the publications I have. I want to thank Dr. Birch and Dr. Petershev for all the help and support. Thank you very much, and for paying for the publication. They're getting really expensive. And of course, I want to give more credits to all my friends, my family, and teammates. I won't get this far without your help. And thank you, my wife, Cecilia. And thank you so much. I think that's all my presentation. Yeah, thank you. Thank you.
Questions from
Yeah.
the auditorium? Anybody online?
Oh, I think so. Do we have any questions? Folks online? Kaki, Enrico? Am I deaf?
Well, don't count with your publication. There's so many that I couldn't even count.
Oh, wow. Thank you. Oh, you know it very clearly.
I'm not the number.
I think I have probably 10 or 11 journals in total, and 6 of them are my first author, and probably 9 conference papers, and a few preprints or in progress works. Yeah.
Very impressive record.
Thank you.
I have a question then. What did you consider most challenging overall? What would you want to be the key message from everyone about the river in the last couple of years?
Most challenging of my work?
Wasn't challenging, no?
No. It's very challenging, but I think the most challenging part of my PhD is actually communication. I think I spent like first 3-4 years to learn how to listen to people, and I'm still learning how to talk or express myself. So I think that's the most challenging part. And also we have had a lot of failures. I have a backup slides which has all the like exploded boards I have. There are just so many, like, yeah. The smell of a burning transistor is very memorizable. Yeah. So yeah, communication and how to deal with failure, I guess. Technical work, I think the power amplifier is my most struggling one. I feel like it's not really mentally challenged. It's not like technically challenged, but mentally challenged a little bit. Yeah.
If you had 2 sentences or 3 as a time message, what you want the people leaving that room, what do you want to be the take-home message of that room? Stay behind. What do you consider your major contribution?
I think I'm very proud of this new topology. I think it could become a big thing. I feel like that could be the only message. Yeah.
Any further questions for now?
Yes, please. Oh yeah. I love buses, but this one is just amazing. Have you ever seen like 2 400 buses running side by side?
Parallel connectivity.
Yeah, redundancy. Yeah.
I have 2 general questions.
Oh, yes, please.
With modular power electronics, it seems like one of the major deficits is switching off because there's more switching.
Yes.
But your 4T topology actually halves the number of switches. So you mentioned that conduction loss is higher, but switching loss is lower. All right.
No. I didn't see the switching loss is lower. I consider switching loss is probably at the same level of any other topologies, because the switching loss is not just proportional to the number of transistors. It's also decided by how much current and voltage you're switching. So if you have more transistors, but they're separating the current like equally, it's probably the same level. Yeah. You're welcome.
My other question is simply, I know you unsuccessful in inserting nanoparticles in brains of mice in order to,
Oh, not really.
or even, well, I was thinking in order to target the magnetic field and where the pulse is stimulated. Has that been attempted to remove?
With TMS, we do have a whole system of neural navigation and to targeting the correct spot for you. But with mice, we basically have a small coil, but it's already covering the whole brain of the mice. So, yeah, I think they're just, yeah, yes.
And yes, it has been nanoparticle activation by magnetic fields has been demonstrated in fruit flies, in mice, and in rhesus macaques.
Yeah.
Using this magnetic field generators that we could work on.
That's what's great. Right, any further questions? Not as you don't want to have a public exam.
Yeah, we can keep it secret.
So in that case, as suggested, we have a short break, maybe of a few minutes, and the committee should ideally stay behind and if we would continue with the exam. And the others can already prepare, hopefully, in case it is successful.
Wow, in case, just in case.
Just in case, yes. Whatever comes after that. Good job.
Thank you.
All right, thank you very much for all of you.
We still have more snacks, and if you like them, please grab more. Wait, are we still recording? I don't know. Are we supposed to?
Yes, you can stop.
Yeah, I guess we can stop.
You stop for this part, yeah.